Okay, so let's say that we again start with a charged capacitor and we charge it to a value Q naught and we attach it to a resistor, resistance R, and an inductor of inductance L. And we want to find how the charge on the capacitor changes with time. Let's say that the value of the resistance R is related to the inductance and the capacitance, let's say as 2 square root of L over C. So that's the value of the resistance. So we know that the general solution is something like this, which of course reduces at t equals 0 to Q naught, which is the initial state. The capacitor is charged to a value Q naught, and that's the value at t equals 0. So what is the A? Well, the A is minus R over 2L plus or minus 1/2 square root of R over L squared minus 4 over LC. But we know what R is, so we get minus, let's put it in here as well. So we have a 2 that cancels with this 2. We have the square root of L over L. So we can simplify that, or let's just leave it like that. Yeah, that's fine. So let's just, at least at the beginning, we'll leave it like that. So we have L over C in place of R. We cancel the 2's. We have let's just do minus 1 over L. Plus or minus 1/2 times the square root of R over L squared. So when we square this, we're going to divide that by L squared, but R squared is 4. We get L by itself when we square this, but we have an L squared on the bottom, so we know we'll get an L on the bottom. We square the square root of C, that'll produce a C by itself on the bottom, and we have to subtract 4 over LC. And so we can see that A just has this first term, which we can simplify by multiplying by the square root of L over the square root of L, and that would give us minus square root of L times square root of L is L. We have L square root of L here, so we just have 1 over the square root of LC. And so the solution is simply an exponential decay, e to the minus t over LC square root. And so if we plot this, here's Q at t equals 0. We have Q naught, and the charge just dies off exponentially like that.